Welcome to The Explainer. Today we're going to embark on a pretty incredible journey to completely demystify the fundamental laws of flat spaces. Honestly, if you've ever looked at architectural blueprints, digital graphics, or even just the tiles on your kitchen floor and wondered about the hidden mathematical rules holding the whole shebang together, well, you're in exactly the right place. Let's explore the strict geometry that literally governs our 2D world.
So to kick things off, consider this question. What actually separates a random doodle in the margins of your notebook from a strict mathematical shape? At first glance, a bunch of connected lines might all just look like geometry, right? But mathematics requires strict boundaries. There's a precise gatekeeper that decides what makes the cut and what is just, well, a doodle.
Okay, let's dive into this. Here's our roadmap for today. 1. The anatomy of a polygon. 2. Classifying shapes and sides. 3. The diagonal formula. 4. Summing up interior angles. 5. The 360-degree exterior rule. And finally, 6. Solving polygon puzzles.
Section 1. Anatomy of a polygon. The basic building blocks. Before we can measure a shape, we obviously have to identify its core materials. Think of this as learning the alphabet before we start writing geometric sentences. When we look at the visual contrast between these examples, true polygons are incredibly neat. They're enclosed. But the non-polygons, they completely break the rules. You'll see open ends where lines just don't meet, you'll see curved lines making circles, and you'll see lines crashing and crossing right over one another. And in geometry, crossing your own lines, that is an immediate disqualifier. No way.
So let's lock this concept in with a formal definition. A polygon is a simple, closed, plane figure formed by 3 or more line segments. Simple just means the lines never cross. Closed means there are absolutely no open gaps. The shape completely traps the space inside it. And line segments mean strictly straight edges, literally no curves allowed.
Moving on to Section 2, Classifying Shapes and Sides, the Geometry Catalog. Once a shape is built and passes the polygon test, we need to categorize it.
So the crucial point here is this major dividing line in the geometric world: convex versus concave. A convex polygon is what we typically picture, right? It's sturdy, pushing outward, with every single interior angle strictly less than 180 degrees. But a concave polygon actually caves inward. It has at least one reflex angle, meaning an interior angle that bends backward, measuring more than 180 degrees. It essentially creates a dent right in the shape.
From there, we just name them by their sides. It's our standard catalog, from the 3-sided triangle and 4-sided quadrilateral all the way up through pentagons, hexagons, and beyond. If a polygon has n sides, we simply call it an n-gon. So a 17-sided shape, that's a 17-gon. Simple as that. Oh, and if you hear the term regular polygon, think of it as the ultimate perfectionist. Every single side is the exact same length, and every internal angle is exactly the same.
Just to ground these abstract concepts in reality for a second, consider this massive number: 604,000 square meters. That is the approximate floor area of the headquarters of the United States Department of Defense, fittingly named the Pentagon. It's literally the world's largest office building by floor area. It really proves how these geometric classifications scale up to hold some of the most complex operations on Earth.
Section 3. The diagonal formula, internal structures. Let's shift our focus to the hidden structural lines inside these shapes.
We're talking about diagonals, the lines connecting vertices that aren't right next to each other. Now, counting diagonals by hand in a square is super easy, but what if you have a 20-gon? You'd be drawing lines all day and probably lose count. Enter the diagonal formula, 1/2 n times the quantity n minus 3. This brilliant little piece of algebra completely saves us from the tedious task of manually drawing and counting lines inside complex shapes.
And this brilliantly illustrates how the math works flawlessly in practice. Let's test it. For a quadrilateral, n is 4. Plug that in, 4 minus 3 is 1. Multiply by 4 to get 4, cut that in half, and you get exactly 2 diagonals. Perfect. How about a hexagon, n is 6. 6 minus 3 is 3. Multiply by 6 to get 18, half of 18 is 9 diagonals. It is so incredibly satisfying to see geometry and algebra work together perfectly like that.
Section 4. Summing up interior angles, the universal law. Now, we're ready to uncover the master mathematical rule that governs the inside of every single polygon.
The logic here is just elegant. Since we already know every triangle always contains 180 degrees, we can basically just figure out how many triangles fit inside our shapes.
A three-sided triangle is just one triangle, so 1 times 180 degrees. A four-sided quadrilateral can be split by one diagonal into two triangles, so 2 times 180 degrees gives us 360 degrees. You see the pattern? Every time you add a side to the polygon, you're essentially trapping one more triangle inside it.
Which brings us to this beautiful ultimate key for unlocking internal measurements. The sum of the interior angles of an n-sided polygon is the quantity n-2 times 180 degrees. If you know the number of sides, you just subtract 2, multiply by 180, and boom, you instantly know the total degrees locked inside that shape. Works every single time.
Section 5, the 360-degree exterior rule, outside boundaries. We've mastered the inside, now let's flip our perspective entirely.
Now, what's really fascinating here is how we actually define an exterior angle. You don't just measure the whole outside space. You take one flat side of your shape and you just keep drawing that line straight out past the corner, or the vertex. The angle formed between that extended straight line and the next side of the polygon is your exterior angle. Notice how each interior angle has a matching exterior partner sitting right there on the straight line. And here is the most shocking, unbreakable law of flat geometry. The sum of the exterior angles of a convex polygon is always 360 degrees. Absolutely always. It doesn't matter if you have a tiny three-sided triangle or a massive, sprawling 100-sided polygon. If you walk all the way around the perimeter, turning at every single exterior angle, you will always complete one perfect circle, 360 degrees. Mind-blowing, right?
Section 6, Solving Polygon Puzzles, Applying the Laws. All right, we have collected the tools, you know the rules for the inside, you know the rules for the outside. Let's put this into practice. Here's our first mystery. We have a polygon, but we have no idea how many sides it has. All we know is that the interior angles sum up to a whopping 2,700 degrees. So, we just work the formula backward. We set our formula, n-2 times 180 equal to 2,700. First, divide 2,700 by 180, which gives us 15. So n-2 equals 15. Add 2 to both sides, and there we have it. Our mystery shape is a 17-sided polygon, a 17agon. Now for the final boss puzzle. Take a look at a complex quadrilateral figure. We have lines extending everywhere. Known exterior angles of 103 degrees and 102 degrees, a known interior angle of 89 degrees, and 2 total mystery angles, an interior angle labeled X and an exterior angle labeled Y. To solve this, we're going to have to combine straight line math with our unbreakable exterior angle law. Let's move to and see how this builds step by step. Step 1, think about angle X and the interior 89-degree angle. They sit on a perfectly straight line together. And straight lines are 180 degrees. So 180 minus 89 means X absolutely must be 91 degrees. Now X acts as an exterior angle. Step 2, we gather all our exterior angles, 102, 103, our new 91, and our mystery Y. Step 3, we know the exterior sum must be 360. Adding the numbers we have gives us 296. Subtract that from 360 and we isolate Y, revealing it to be exactly 64 degrees. Aha, puzzle completely solved.
So, we've just uncovered the exact rules that govern every single flat space in the universe, from basic doodling to the architecture of massive office buildings. But I want to leave you with a provocative thought. If these simple 2D rules strictly govern all flat shapes, how do you think these mathematical laws scale up when we enter the third dimension? Or what happens to these rules if a shape literally has an infinite number of sides? Keep questioning those boundaries, and thank you so much for exploring these concepts with me on this explainer. Keep learning, and I'll catch you next time.